In this second lecture file on GPS, we'll look at accuracy of data. First of all, it's important to be aware of the three different levels of accuracy and categories for GPS systems. One is the commercial level, the second is mapping grade, and the third is high precision. Commercial grade GPS systems would include phone and car navigation systems with accuracy of the range of 3 to 10 meters. Mapping grade devices include GPS devices with 1 foot to 3 meter accuracy, and potentially less than 1 meter accuracy with post-processing or real-time correction. High precision GPS systems would include sub-foot accuracy as dedicated high-quality GPS devices which use base stations and RTK, such as the use of highly accurate GPS system in surveying. Several variables are important when looking at levels of accuracy. The time spent on the measurement of the data being collected, the design of the receiver, whether or not post-processing is being used, and the relative positions of satellites, which is technically known as PDOP, position of dilution of precision. There are three different methods of positioning: autonomous, differential, and phase differential. First of all, autonomous data collection involves 10 to 20 meter positioning. Differential would include 2 to 5 meter ranges of positioning, and phase differential would include centimeter ranges of positioning. Next, we want to look at the Wide Area Augmentation System, or WAAS. WAAS provides free GPS differential correction data for visible satellites. It was developed and is operated by the FAA, Federal Aviation Administration, for flight navigation, but it's also available for free for GPS users. WAAS-enabled receivers can provide sub-meter level accuracy anywhere in most locations of the United States and southern Canada. WAAS includes differential corrections, which are computed from ground stations and then uploaded to geostationary satellites for broadcasting. WAAS-enabled GPS receivers automatically use such correction data to enhance the positional accuracy. When we look at sources of error, there are three major categories you need to be aware of. The first is multipath errors, then PDOP errors, and then SNR, or signal-to-noise ratio errors. Multipath errors occur when GPS signals arrive at the receiver having traveled different paths. Here's a good example. The interference of a building or large object, a surface near the receiver, can cause a multipath error. Positional dilution of precision, or PDOP-related errors, exist when you have a poor PDOP rating. A poor PDOP rating results because satellites are not spread relative to the receiver in an effective manner. So if the satellites are in effect bunched up together relative to the receiver, you will expect to have lower PDOP and thus potentially could have errors. Signal-to-noise ratio determines the signal strength relative to the noise. GPS position is degraded if the SNR of one or more satellites in the constellation falls below a certain range. Signal indicators are found on GPS units, such as the bars that are shown at the bottom of the screen. Next, we'll take a look at GPS data coverage. Cell phone technology plays a critical role in the improvement and accessibility of GPS signals and potential for data collection. So we'll take a look at differential GPS coverage and its relationship to cell phone technology. We'll take a look also at improvements in receiver technology in recent years, and then in the marketability of this system. This map shows the current differential GPS coverage for the United States and Canada. It's highly dependent upon the location of cell phone towers, as we'll see in just a moment. Differential GPS range can extend to 250 miles, but local conditions often limit it to as small of a range as 25 miles. The coverage depends in part on the physical landscape, so large obstructions, mountain ranges, and so on can get in the way of differential GPS data availability. Coverage may be boosted through increasing the number of towers that can deliver differential GPS signals, or through local techniques such as setting up a ground station to boost coverage for a particular project. This shows several of the major cell phone coverage maps and the availability of differential GPS as of a couple of years ago. Differential GPS stations can be relatively inexpensive at low power and can be used to boost signal strength and availability of differential GPS in areas where otherwise it might not be an option. So as we look at differential GPS coverage, DGPS coverage, are the benefits worth the cost? On the yes side, we see extra coverage in rural areas coming along. New towers are not needed in areas that have existing coverage. This DGPS can be added to existing towers. High-power DGPS could potentially penetrate buildings and has potential to bring location services to many new environments. This would benefit government and also private industry, where industries need and want better location services. On the negative side, there are still substantial areas of the United States where low population densities exist, which are not covered by DGPS. And where cell phone companies may not be compensated, there needs to be a better plan for DGPS expansion in the future. We've seen several major advances in receiver technologies, such as the development of smaller screens, touchpads, full keyboards, and long-lasting batteries. This looks like something out of a historical technology museum at this point, but this Palm device here is only 10 years old, or maybe even more recent than that. Internet connections are getting better, and you have the capacity to stream video as well. Batteries are much better, chargers are easier to use, and they're power conservation modes. Data-heavy devices tend to use a lot of power. And so with using that power, these advances in battery technology and so on have been very important in making the handheld devices more available to the public and potentially then increasing the use of global positioning systems. So this means that devices are easier to use, batteries are longer lasting, data is being updated much more frequently, and real-time data plotting is now possible. But there are still problems. As many of you know, if you have an iPhone, for example, which tends to use batteries very quickly, there can be strains on batteries, costs of services and roaming and data charges, the need for larger receivers. Solutions exist, but they cost money, and they can involve, if you are in the position of a business or a government agency, sometimes that's a factor that has to come into consideration as well when thinking about the use of global positioning systems. So this section was intended to just give you an overview of some of the relationships between different types of mobile service technologies and their relationship with GPS.